Part B, using correct units, explain the meaning of the definite integral. So it's the definite integral from t equals 0 to t equals 40 of the absolute value of v of t dt in the context of the problem. Approximate the value of that integral using a Wright-Riemann sum with the 4 subintervals indicated in the table. All right, so let's first tackle the first part. So what's the meaning of this definite integral? So the velocity is a vector. It has direction. And you could see when you look up here that sometimes the velocity is positive and sometimes it is negative. And a reasonable interpretation of that is, well, this is when she's walking in one direction, and then that's where whatever direction we assume is the positive direction, and this is when she's walking the other way. And so she has a positive velocity here, and then she has a negative velocity. She has some speed in the other direction, and then she has a positive velocity again. So if you were to take the absolute value of this, if you just cared about the magnitude of the velocity, well, we're talking about speed. But we're not just talking about the absolute value of velocity. We're integrating the absolute value of velocity over time, from time equals 0 to time equals 40. So if you integrate speed, if you're saying, okay, for every little amount of time dt, she has some speed, well, that's going to give you the distance that she travels. So the distance, remember, is the difference between distance and displacement. Is displacement you can think of as the net distance. It takes, if you go back and forth a bunch of times, it's going to add up to the distance, but they're going to net out with respect to each other in displacement. So this right over here is going to give us the total distance, not displacement, that she travels over those 40 minutes. If there was no absolute value sign here, then we'd be talking about the displacement. And so let me write that. So this integral from 0 to 40, absolute value v of t dt, is the total distance she travels over the 40 minutes. Over the 40 minutes. Remember, our unit of time here is in minutes. All right. So using correct units, and so the units, let me write it this way, is the total distance she travels over the 40 minutes. The units are meters. The units are meters. All right. Then they say approximate the value of that integral using a Wright-Riemann sum with the 4 subintervals indicated in the table. So what do they mean by a Wright-Riemann sum? Well, actually, let me just draw the absolute value of v of t. And I already took the trouble in the last part of drawing the axes. And you wouldn't actually have to do this on the test, but I'm doing this to just help you understand what we're actually going to do when we talk about a Wright-Riemann sum. So in orange I have v of t, but if I want to do the absolute value of v of t, I'll do that in magenta. So the absolute value of that is that, absolute value of that is that, absolute value of that is that. Absolute value of negative 220 is going to be positive 220. So we saw here when t is equal to 24, v of t is negative 220. She's running in the opposite direction or jogging in the other direction, but we're going to take the absolute value of that. So when t is equal to 24, her speed, we could say, is going to be 220. We're going to take the absolute value of it. So it's going to be right around there. And then the absolute value of this is just going to be that point again. And so we don't know the actual velocity function. The actual velocity function, I don't know, it might look something like this. It goes like that. Maybe it dips down. Or I should say the speed function. We don't know the actual speed function. So this is the absolute value of v of t, which is the speed function, you could say. Speed function. And so if we wanted to actually integrate it, well, we don't know how to do it if we don't know how to do it exactly without knowing the exact function. But we can approximate what the integral is going to be with a Wright-Riemann sum. And a Riemann sum is just breaking up this area into rectangles and then finding the total area of those rectangles. And then there's a couple of ways you could do it. You could use for each rectangle, you could use the left boundary as the height, or you could use the right boundary as the height. And so they tell us to use a right Riemann sum. A right Riemann sum. So for each of the rectangles, for each of the intervals, we're going to use the value of our function on the right side to approximate the area. So let's do that. So let me divide this into 4 rectangles, and they give us the 4 intervals. So one interval goes from 0 to t equals 12. We see that there. The other interval goes from 12 to 20. The next interval goes from 20 to 24. The next interval goes from 24 to 40. And if the whole notion of a Riemann sum is completely foreign to you, I encourage you to watch the videos on Khan Academy on Riemann sums. And so here we are. So the first interval is from 0 to 12. And so we want to use the value of our function on the right side to define the height of the rectangle. So let me define. So that rectangle is going to look like this. So that's a rectangle right over there. Then the next interval goes from 12 to 20. The next rectangle goes from 12 to 20. We see that there, from 12 to 20. So let's use the value of our function at 20 to define the height of this rectangle. So just like that. Look like, let me do it. You just hand draw that. It would look like that. And then the next rectangle goes from t equals 20 to t equals 24, and we want to use the right-hand side to define the height of that rectangle. And you can see it's a little irregular, and that's okay. They all don't have to have the same width. So the height is something like this. And then the last interval is t equals 24 to t equals 40. And so we use the right side as the height. So the interval, so this was the last interval we did. The next interval is going to be that. And then the height, we use the right-hand side to define the height. That's why it's a right Riemann sum. And so our approximation of the integral of the absolute value of v of t is going to be the area of these rectangles over here. And so we could write the integral from 0 to 40 of the absolute value of v of t dt is approximately what's going to be this first change in time times this height. So this first change in time, this is a change in time of 12 times, so it's going to be 12 times, what's the height? Well, v of 12 we knew was 200. V of 12 is 200. So it's going to be 12 times 200 plus, okay, the height here, or the next interval goes from 12 to 20. So it's going to be 8 times, and then the height here is going to be, what is v of 20? I think that was, v of 20 was 240. V of 20 was 240. And then the next interval goes from 20 to 24. So that only has a change in time of 4. And then what is the height at 24? The height at 24. And remember, we took the absolute value of v of t, so it's 220. So 4 times 220. And then our last rectangle, our change in time, we go from 24 to 40. So our change in time is 16 times the height at 40. What was that? That was 150, I think. Yep, that was 150. So times 150. 150. And so just to make clear what I just did, I'm just adding up the sums of the areas of these rectangles. The area of this rectangle is 12 times 200. Area of this rectangle is 8 times 240. The area of this rectangle is 4 times 220. Area of this rectangle is 16 times 150. And then let's see, we could calculate that. We're not allowed to use our calculator for this part, so we're going to do it by hand. 12 times 200 is going to be 2400 plus 8 times 240, that's going to be 1600. 1600 plus 3200, that is 1920. Did I do that right? 8 times 40 is 3200. Or sorry, 8 times 40 is 320 plus 1600. Yep, that's right. Plus, this is going to be 880 plus, let's see, 15 times 15 is going to be, would be 2250. That would be 15 times 150. And so we're going to have another 150. And so this is going to be 2400. 2400. whoops, is 2,400. Now we want to add all these together. Let me just do it the easiest way. 2,400 plus 1920 plus 880 plus 2,400 again, plus 2,400 again, will give us, we get a 0, we get a 10. So let's see, we have 9 plus 9 is 18, plus 8 is 26, and then we have 7. So we get 7,600. So it's equal to 7,600. And just to be clear, this would be in meters. In meters. In meters. Now you might be saying, wait, didn't we just find an area? Wouldn't areas be in meters squared? But remember, we're finding the area under the velocity graph. And so if you look at our units, say for this rectangle right here, you're multiplying 12 minutes. You're multiplying 12 minutes times 200 meters per minute times 200 meters per minute. So when you multiply them out, the minutes cancel with the minutes, and you're left with 2,400 meters. So even though it's area, if you look at the units, it's going to be in meters, not meters squared.